nós dando continuidade aos seminários do nosso departamento da Cotel, que acontece às quartas-feiras, semana sim, semana não. Hoje nós temos o prazer de ter o professor Francesco Toppan, do nosso departamento, que vai falar sobre primeira quantização de férmions de Majorana Braided. E seja bem-vindo, assim, um prazer. Toppan.
Obrigado pelo convite, Nami, pela possibilidade. Eu vou agora trocar imediatamente, switch to English, because I take the opportunity that this seminar will be broadcasted in the YouTube channel of CBPF, so it will be profited for collaborators and researchers who are interested, who are not only in Brazil, but also outside. So, and that's why I decided to give this talk in English. So now I try to start the share screen. I hope everything is working. Let me do. Okay, this way. And enter full screen. I hope everybody is seeing, right? Okay. So now, okay. Today's talk is about this work. This is a very recent work, in fact, that I posted in archive 2 months ago. And you see very quickly has been accepted and published in Nuclear Physics B. Just a few days ago appeared the online version of this paper. And what is about? It is based on some first principle, is the first quantization of some objects which are the Majorana fermions, which are braided. And I will tell you first the main motivation for the work. One of the main motivations came from a proposal that was put forward by Kitaev some 20 years ago. So in condensed matter, we know that there are some collective modes which are emergent and can be described by some particles which are fermions of Majorana type. They're real, so they coincide with their own antiparticle. They appear in condensed matter. And the Kitaev's proposal was to use this kind of Majorana fermions to make something which is a topological quantum computation, topological quantum computer. The idea is that if you use ordinary quantum bits as the quantum computer that now are made by Google and by other companies, there is a big problem because in order to make it working, they need to be, the quantum bits need to be entangled. And people know that the interaction with the environment produces a decoherence which can, in many cases, destroy this entanglement. So this is quite a challenge. And Kitaev's proposal, we'll come back a little bit, was that you use Majorana fermions just to offer some topological protection from this decoherence. There is a very well-known research that investigated a lot of aspects of braid groups and knots that has a series of papers, in fact, discussing the knot logic and the topological, underlying this topological quantum computation. In particular, for instance, in this kind of work, it's one of the most complete, but there are several by him in the literature, in archive. So, what my fundamental ingredients, in fact, this paper could have been done some 25 years ago, because the fundamental ingredients are already contained basically in these 2 papers that you can see here. This is a seminal work, appeared in Communication Mathematical Physics some 30 years ago by Kaufman and Saller. So about 3 fermions and not polynomial, a specific one, which is the Alexander Conway not polynomial. This is one first ingredient. And the second ingredient is that contained in the book by Majid and some approach to parastatistics using some Hopf algebra structure endowed with some peculiar framework, which is the braided tensor product. I use this kind of two ingredients. The second ingredient, by the way, I got very familiar because last year, and I even gave a course at CBPF, at the School of CBPF. I published two papers in Journal of Physics A using this framework of Majid and proving some result that was not known at that time, working some specific model. I succeeded to prove that there are some Z2 parafermions and parabosons that are theoretically observable. And this was some kind of algebra introduced by Rittenberg-Weiler some 45 years ago, and nobody attempted to do that. And with this tool, in some simple model, can prove that. So using this tool of Majid. And this is some generalization about this kind of tool. Now, first of all, I have to say what are braids. I don't give the definition, but just present some pictures. So everybody is familiar with the permutation. The permutation, you take some particle, you just exchange the position. But braided do something a little bit more refined. You follow the path when you braid two particles. So these are some examples. You have as a particle which can be red, another is blue, and then you can exchange the position, and the blue can cross the line of red before or after. And the basic relations are encoded in this basic relation here. You can see. You can deform with continuity this strand, and you have this type of relation here, basically. This is the definition, mathematical definition of the braid groups. And this is another example of braid, where you have this kind of strand. You see from bottom to up. And the particle can make some loop around each other this way. And there exists a connection of braid with knots. Take, for instance, any of these strands, and now close this strand, the end point, so the initial point with the end. So follow my pointer. You can close this way, the blue with blue, the yellow with yellow, the red with the red. And if you close this way, you go from braid to this kind of figures. And these kind of figures are knots, which have a very fascinating story, both in mathematics and in physics. So they're widely studied. In fact, in physics, it was Lord Kelvin that at the end of 19th century proposed to describe atoms in terms of knots. And there are a lot of activity, even today, concerning skyrmions that use this kind of structure. And the point of this knot is why they are topological, because you can deform them with continuity, but you cannot go from any of them which are listed to the other one unless you cut one of these string and you join back together. So that's not possible. This is why they're topological. And this is exactly the idea which Kitaev took. You know, the coherence is related with the interaction with the environment. And if the interaction, but if you encode in some topological way, like this one, you can make the interaction small enough in such a way that you perturb locally, but the topological property, unless you do something very bad like breaking them, they are preserved. And if you use that, you can encode this logical operation using not ordinary quantum computer, which use qubit, but a topological quantum computer, which uses some knots, some braided element. So this is the idea behind. So far, so good. And I want to say something also for the student, which is the following. there are some technical parts which will not enter into much detail, but I want just to stress why this is important. But first of all, let me say what is a Majorana fermion. A Majorana fermion is something absolutely very simple. First of all, is a fermion. Second, is a real. Real means that basically it coincides with its own antiparticle. And the simplest example of a Majorana fermion is described by a two states. One state is the vacuum, which is bosonic, and the other state, which is here is known as C, is a fermionic excited state. And technically, you can say that the fermions, this kind of fermion, one Majorana fermion, is a Z2 graded qubit. Why Z2 graded? Because it is partly bosonic and partly fermionic. And on this object, you have four operators that act. The diagonal one, alpha and delta, are bosonic, and beta and gamma, which is the anti-diagonal, are fermionic. And together, they satisfy some superalgebra in terms of commutator and anti-commutator, which is these blue brackets here. And this structure, well, mathematically is known as a GL11 superalgebra, decomposing even part and odd part. Now, these matrices gamma and beta are something that every physicist knows, because there are just the creation and annihilation operator of a fermion, which satisfy this condition. Gamma is the creation operator, beta is the annihilation operator, which annihilates the vacuum. Gamma creates the excited state, and this is just a fermionic oscillator. Now, there is an important property in quantum mechanics, and the important property is that the bosons and fermions are superselected. And what does it mean? It means that you can mix bosonic state together, you can mix fermionic state together, but you cannot mix bosons and fermions. So you don't construct some mixed state which is partly bosons and partly fermions. This is the rule of superselection, which we know apply on all these theory containing bosons and fermions. So if you do that, this kind of system has described by this kind of Hilbert space C11, which means that it is graded. But you have to take into account that the physics is not described by the Hilbert space. The physics is described by the projection of the vector of the Hilbert space, because what is physics is not the amplitude of a wave function, but is this modulus squared. So you take out the phase of this, and if you take out the phase, what you get is the Bloch sphere. For the ordinary qubit, the Bloch sphere is a two-dimensional sphere described by Bloch, which means the inequivalent physical configuration of the space, of the state. And what about in this case for Majorana? Well, if you eliminate the phase and you cannot put together, you have just one state up, one state down, which are just Z2, which means that ordinary one bit of information described in this way. And this is the Bloch sphere of a single Majorana fermion. So, and you can describe the Hamiltonian like this operator here, which tells you that the vacuum has 0 energy, and you can create the excited state as one quantum of energy. This is very simple. Now I do first quantization. First quantization is something people do all the time. You take a single particle quantum Hilbert space described by a Schrödinger equation, let's say, and then you construct the non-interacting model of n states by taking the tensor product of these, and in the ordinary case, either you symmetrize, totally symmetrize, or totally anti-symmetrize them. And the space in the first quantization of n particles is included in the tensor space of a single particle taken n times. And the vacuum is always the tensor product of the vacua of the single particle. This is the n-particle vacua. Now, this kind of point that it is a little bit technical, unfortunately, and you see, this point is not taught in the fundamental courses in physics, even if it should. And why it is not taught? Well, because basically when you introduce a Schrödinger equation, and then you ask, okay, you take a single particle state, then how to make first quantization using the multi-particle, and people know how to do to totally symmetrize or totally symmetrize in case of bosons and totally anti-symmetrize in case of fermions. People know how to do that by hand. But if you want to do something more sophisticated, there is some ingredient that you should use, which is the Hopf algebra. Hopf algebra is not complicated, just simply because in general, physicists are not used to work with that. And in the Hopf algebra, there is a structure, which is the coproduct, which tells you exactly how to symmetrize, totally anti-symmetrize, or do something different, as I showed. This is the main point. So it allows to construct the coproduct is this operation. I don't enter into detail because I just want to give the main idea, because the details are simple, by the way, and I have a lot of results to discuss. So it is a state which tells you how to go from one particle to construct the tensor product of two particle state. And since there is some property which is called co-associativity, from two particle state to three particle, four particle, n particle, and so on and so on. This is the main idea. And the other main idea, there are some operations that are given here, which tells you how, for instance, you have some creation operator in the single particle case, and how this creation operator for the single particle act in the tensor product of two particles. This way, using this kind of property. And with this kind of property, you can construct the Hilbert space of n non-interacting single particles. You can repeat all the construction, total symmetrization, total anti-symmetrization in this language, which is quite useful. So, and here I give you the example. If delta is the Hamiltonian for just the single particle, the Hamiltonian Majorana fermion, the Hamiltonian for the two particle case is just given by the sum of these tensor product. This is a 4x4 Hamiltonian because the single particle Majorana fermion is a two component. When you take two of them, tensor product, you have 4x4. When you have three, you have 8x8, and so and so. And this is how you can construct the creation operator acting in each kind of state. And now the key ingredient. This is the key ingredient which was introduced by Majid in 1995. And the key ingredient is simple like that. So if you have four elements, A, B, C, D, which represent, let's say, represent some operator. Now, if they are bosons, it is very simple. You take this and you make A tensor C times B tensor D in the standard rule. But if they are not bosons, you have something different. You have to tell how to braid this guy, B and C, in something which is known as the Braided Matrix, which is a n squared times n squared matrix. In the simplest case, if these are fermions, and people who work with fermions know that each time you change one fermion, the position of one fermion with respect to another, you have to put a minus sign, you have to put a minus sign. But in more complicated cases, and in the braidization, the true braidization, a minus sign is not sufficient. You have something more general. This something more general that can be used in this framework, and it was people didn't. So the construction was there, but it was not used. It's just to take these graded Majorana fermions and make a consistent braidization of the creation operator of two Majorana fermions by using this kind of operation here. So you have something which is a braided matrices, BT, that I will show you in the next transparency, which is a 4-10-4 matrix, which satisfies the braiding condition put forward by Majid to make a consistent this kind of structure. T is a deformation parameter, and I will show you in the next transparency this kind of matrix which is given here. This matrix is nothing new, by the way. This is the same matrix which is contained in the Soler-Kaufman paper of '91 in communication, exactly the same. This is R matrix of the Alexander Conway polynomial in the crystal rep basis, technically. And what are these properties of this matrix? T is a parameter which lives in the complex plane, and if you eliminate the origin, the punctual complex plane, this matrix is invertible for any T outside the origin. At the origin, you see this column and this row is of 0, so it is not invertible. This matrix is related with the Bourau representation of the quantum group of the universal enveloping algebra of GL11. And the basic point is that the consistency is that this matrix satisfies, and you can easily compute that, this braided relation. So this is a relation in the 8x8 dimensional space because BT is 4x4, identity is the identity 2 by 2, and this tells you how 3 Majorana particles can be braided in the first, in the second, in the third, and you can make first the braiding of the first and the second, then the braiding of the second and the third, then again the braiding of the first and the second, and this is the same result as braiding the second and the third, first and second, and the second and third. So this is the basic property of this. There are some other interesting properties about this matrix, which are compatible with the dynamics, because if you take the Hamiltonian operator for the two particles, it commutes with this matrix. This is another consistency condition. The other consistency condition is that the n particle Hamiltonian always create with the n particle creation operator. The n particle creation operator creates one quantum of energy due to this relation here. You may be puzzled about this choice of this coefficient here, but this matrix is bosonic. In general, people will work with fermions, and they put bosonic matrix in the block diagonal form and fermions in non-block diagonal, but in this case it's not like that. But you can easily see that if Majorana fermions are given by bosons which are given by these dots here, and fermions are the star, when you take the tensor product, you accommodate bosons and fermions in this kind of structure. And then you can see that the non-vanishing entries of BT correspond to the bosonic entries. So this matrix is bosonic. So this satisfies all consistency conditions which are required. So once we have this, we can study what is the physics of that. So this is the point, this is the invertible matrix. You can construct this, and you can construct with the rule of the coproduct the n particle state, and you have a state which are partly bosons, partly fermions, and they have the level of energy. We'll come back later on this kind of transparency. Now, if you have this matrix BT, you can ask what happens when you take this BT and you braid the particle 2, 3, 4, n times, and you get this kind of relation, which are some very simple relation to solve recursively in terms of these recursive polynomial here, which are given by this kind of expression. You can solve very easily using some combinatory, some induction proof. It's also big deal. But then the important point is the following. You ask the question, what happens if you braid the particle, you make n loops around, and you get back to the identity? With a single matrix, you cannot do that because B1 obviously is not the identity, but B2 get the identity, B3 can get the identity, and so on and so on. And this kind of question has also a solution. It is given by this polynomial. These are recursive polynomials that enter. You have B1, B2, B3, B4, B5, and it is pretty obvious how they generalize. Each time you get some extra element, okay? The next one, B6, you add a minus B5, and so on and so on. Now, the root, the condition which tells you that after n times you get the identity are related with the roots of this polynomial, when this polynomial goes to 0. And you can prove two things, that any root of these is a root of the identity, which means that t to some power is the identity. And conversely, all root of the identity are solutions, are root of some of these polynomials. There is a unique exception, which is t minus 1. And why this is an exception? Because if you plug t minus 1 here, you can see you get, for B1, you get 1. But for B2, you get 1 minus minus 1, which is 2. For B3, you get 1 plus 1 plus 1, which is 3, 4, 5, and so on. So t minus 1 is never a root of any of these polynomials. It means for t minus 1, Bn at t minus 1 is never the identity. Okay, this is just some sketch of this proof, okay, I can skip that because now this comes the question. Okay, everything is good, but now we have this kind of framework. What this kind of framework tells about the physics of the model. And here it comes something which is the truncation of the spectrum at the roots of unity. So if I use these braiding matrices and I take here the creation operator gamma of the single particle Majorana fermions, I get that the braiding of these two creation operators, one tensor gamma and gamma tensor identity, is given by this formula here. And this formula tells how the excited state behave in this framework. So this is an example. For the first particle state, I have a creation operator gamma, and gamma squared is 0 because I show you in this transparency, this is a fermions, creation operator of fermions. You cannot get two fermions in the same state. This is the Pauli exclusion principle. So gamma squared is 0. Now, in the two particle case, you want to create an excited state for two fermions. Instead of taking gamma, you have to take identity tensor gamma plus gamma tensor identity. And what about in the two particle case, the two excited state? It is the product of this. And what is the product of this? It gives that with this kind of rule. If you open up this computation, you have some part which vanishes because gamma squared is 0, but then there's some part which are there. And then if you follow this kind of braiding here, this non-trivial braiding, you ended up with this kind of right-hand side. And now, what is this kind of right-hand side? if t equal 1, and t equal 1 is exactly the property of ordinary fermions, this right-hand side is 0. And this encodes the property that ordinary fermions satisfy the exclusion principle. So even if you take 2 of them, you cannot create more than 2 fermions in the same state. But if T is different, this is non-vanishing. And then you make the same analysis, a little bit more complicated from the combinatoric point of view, but not so much. You take the creation operators of the n-particle state. You take to create the excited state of k energy level out of these, taking the power of them, and you realize that you end up with some operators times some factor here. And what is this factor? This factor is the product of the polynomial entering before. How does it work? So, okay, this is some example of this computation. This is just some fun. You can just technical combinatories. You can put the boxes, and you can see that when you braid all these, you get some polynomials entering this type, and you have this kind of structure. So, and here you see that you have these the first polynomial, the second polynomial, the third polynomial. Sorry, this is the polynomial B2, this is polynomial B3, this is polynomial B4, they appear as a factor. So you have the product of that. So this means the following, that when you take a particle state with k energy level, it is the product of three parts. The n-particle vacuum, some operator acting on the n-particle vacuum, constructed with the creation operator of the, in this case, of the fermions, and then some factor here where you have some the polynomial, this recursive polynomial enter. This is the product of the recursive polynomial. And obviously, if one of these polynomial is 0, this factor is vanishing. But if this factor is vanishing, this tells you that this vector, which in principle could be there, it is not there. And so this gives the truncation of the spectrum. So this is something very simple like that, right? And now we come very interesting notion, and I come back on that, which is the notion of level of the root unity. I told you that all these recursive polynomial have some solution which are root of unity, but then you have to organize the root of unity in a clever way, making the root of unity when the root of unity appears for the first time as a solution of one of these polynomials. Why this is important notion? Because this tells you how the spectrum is. I give you an example. You take this polynomial here, B6. This B6 has 5 roots. And these 5 roots are organized in this level. One root already appeared for the second polynomial, this root of t squared equal 1, which is there. Other root appear with the t cube equal 1. And then there are some 2 extra roots which appear here. What is the physical significance of this level of the root? There are 2 physical significances. One tells that the truncation of the energy spectrum. A root of level k accommodates at most k inequivalent level energy levels in the multiparticle state. And there exists also a statistic viewpoint which tells you that the root of level k implies that at most k-1 Majorana parafermions can be created. The lowest case is when k equal 2 at t equal 1, and this tells you that you get ordinary Majorana fermions that satisfy the Pauli exclusion principle. So that's why it is an important notion directly related to physics. And here I give you the case. So up to level 4, the root of unity are always in this, belong to this red circle of radius 1. What is this point x? This point x is -1. Remember, -1 is a root of unity, but it is only root of unity which is not a solution of a recursive polynomial. This corresponds to the spectrum which is fully non-truncated. This is the special case here, -1. +1, which is here, corresponds to the standard ordinary fermion. The root of level 3, they are here, they are here. Root of level 4, they are here and they are here. They are also here and here, but these which are there, they are not already appear at the level 2. So these root have 4 states, while this has only 2 states. You can go further. You can go to the level 6, and you see how these extra roots are organized. You can go to level 8, and it is clear how this situation appears. Now, I told you that there exists this parameter t which braids. This parameter t can belong to any point in the complex plane outside the origin. But as far as the spectrum of the theory is concerned, you can just work with the root of unity. And why is this so? Because the untruncated spectrum coincides with the spectrum of t equal -1, which is here. Any truncated spectrum is one of the roots entering here with their own level. So without loss of generality, you can just fix to be t is a root of unity, living in this circle, in this way. Now, let me present some table to illustrate the feature. This blue table here tells how many n-particle Majorana state I construct when I take the level 2 root of unity, which is equal 1. And in that case, due to the Pauli exclusion principle, I can only have 0, which is the vacuum, and the first excited state. And that's all. I cannot create anything more than that. If I take a level 3 root of unity, something different appears. I have a truncation, but the truncation is a step further. You see, when I take a 2-particle, 3-particle Majorana, and so on, I can construct an extra excited state, which has level 2. Instead of having just 2 states, 0 and 1, I have 3 states, 0, 1, and 2 excited states. If I take a level 4 root of unity, you can see that I have a plateau, but the plateau is shifted of one unity and I have it here. For level 5, the plateau is further shifted in this way. And you can see that this framework is general. Okay? So all root of unity, which gives truncation at some level, give this plateau. The only exception is t-1, which can be considered level infinite root of unity because it grows linearly, the number of states, there is no plateau for this. And this is the whole possibility that we have for this kind of model. Now, I find it interesting to associate the root of unity levels with fractions, and I will explain you why. So remember that t should belong to the unit circle. So I can represent it with some angle theta, which go from 0 to 2 pi. And since this is a root of unity, it should have some coefficient, which is a fraction, f, which belong to 0 and 2. And this is the fraction. t-1 is given by the fraction 1 because this is -1 is e to the minus ip. L2 given by 0 because 1 you can put theta equals 0, f equals 0. L3 has this kind of structure, this kind of fraction, L4, L5, you see the two extra solutions of the polynomial B6. 3 of them were already in L2, L3, but the 2 extra, which gives this 6-dimensional space, are these ones, and so on and so on. So why I did that? Okay, because there is some possibility, of course, which is open to, to claim, okay, let's say, what happens if this theta is an external control parameter? I don't tell you how to do that, but it's an external control parameter which can be manipulated to engineer braided Majorana-Fermions. That's a possibility. And the output of this theta is not continuous, and you can see that it jumps at the root of unity in some, it looks like some random way. You see, this is, it feels, if you remember here, it feels this in this way, and there are more and more root of unit here or higher level which enter here from this to here. So you see that L5 is here, then you have L7, etc., etc. And this, of course, is reminiscent of something, and this is reminiscent of something of the fraction that enter the fractional quantum Hall effect. Probably they're not the same. Some qualitative features can be grasped in this way. So, concerning this system, I can also mention about the Bloch sphere, generalized Bloch spheres. I already told about fermions and bosons that are super selected. And now you can ask the question, what is the Bloch sphere of this multiparticle sector? Okay. And these are some answers. Okay. So if you take the simplest level, which is ordinary fermions, as I say, you cannot do anything. You can get only 2 states, which means that the Bloch sphere is just, if you take the generalized Bloch sphere, is just Z2, which means just 1 bit of information. So if you have Majorana fermions, you can make any particle Majorana fermions, but you don't braid, you assume just ordinary fermions, you don't have any quantum computation, because they are just represent 1 bit. In order to have some topological quantum computation out of that, you have to construct this braiding somehow. And already at the level 3, root of unity, you can get a qubit in the bosonic sector. This is the bosonic, the S2 Bloch sphere. At level 4, you have the qubit, the Bloch sphere appear both in the bosonic sector and in the fermionic sector, described by Y. And from level 5, you have also the generalized Bloch sphere, not of a qubit, but of a qubit. So that's how you do that. And this was my comment. Besides, I can mention the following. So I have a lot of discussion, by the way, on this. I asked some specialists, what does it mean? Indeed, observation was done before. Because root of unity, everybody knows that there are special truncations in the representation theory of a root of unity. So I said, okay, I never used the representation of the quantum groups. This is obtained by some different type of combinatory, but there should be a relation, and probably this relation was already observed. So I started asking some specialists, like Majid. He said, okay, I have this kind of, here's the same kind of recursive polynomial that you have. I have here, okay, but so I didn't notice this. I didn't. So he was not motivated to check that. I asked Reshetikin about that. I found it interesting. I don't know, because I'm not working so much in root of unity. I can give, this is my student, former student, a PhD student that work on root of unity. So I asked him, and he answered, it seems that there should be related with the Reshetikin to arrive with an invariant at the root of unity, this sort of thing, but he was not, it's not sure. And I asked, oh, I have to think with other person that because to see what these. So it could be even some new observation about that. By the way, this paper I sent was published. I sent to Nuclear Physics B, and why Nuclear Physics B? Because the editor of session is Saler, and I was thinking that it was appropriate for him to deal with this kind of paper and this kind of things. So this is exactly this kind of open question that I have, and I'm still discussing with specialists on that about what is the meaning of that, because this is there, and if it's being observed or not, but physically has very important consequences because it tells the dimensionality of the spectrum and also tells how you need to do this kind of operation of braiding to really construct, if you are able to, a topological quantum computer based on braided Anathernia. Now, one point I want also to mention is the following. Of course, I gave you some fractions. People know that the fractions appear in the fractional quantum Hall effect. Okay, and maybe you have to find this kind of fraction with some more general construction based on these similar argument, generalizing these matrices with the Burau matrices 4x4 that, as I mentioned before, was taken from this Kaufman-Saler. This is the appropriate matrix for this kind of simple model with the Anathernias, which are Z2 graded qubit. Okay, so I want to advertise some very old result. In fact, 30 years ago, I went to some postdoc in Germany. I had a contract there. So I should have visited Rittenberg in Bonn, in fact, but he was not there. So I decided, okay, let's say the first 6 months to visit the mathematical department at University of Frankfurt am Main. So Frank Constantinescu was working. Then I moved to Bonn, the other man. I never met Rittenberg there because he was always traveling anyway. So, but with Constantinescu, in fact, we used as a very mathematical result. We took the artificial representation of braid groups, which is applied on free groups. And we combine this with something which is the Magnus representation of free groups. And when you do it with something which we call the linearization, so a representation of the braid groups with some matrices which are constructed with the braid group itself. It looks like fancy, strange, but this has some deep implication because you can plug on these some representation of the braid group, for instance, the trivial one, and you get a new representation. So, and with the Mirko Lude, who was at the time was a PhD student of Florin, we proposed the notion of the braid lifting. So starting from the trivial representation, go to the further representation of the first level, which we got exactly the Burau representation that is used for this matrix. If you do now the Burau representation and apply another lifting, go to the second order, you produce the Lorentz representation of Hecke type of the braid group and so on and so on. These papers are okay. So they're mostly mathematical, so they have some citation in the literature, but I think there could be profited more than has been done, in fact. And the essential ingredient, of course, can be applied also more general to see where other type of fractions that can enter, maybe in relation with the fractional quantum Hall effect as well. So my final transparency is about this. I discuss about first quantization. And you know that when you take a Schrödinger equation, you have two approaches that you can make. This is the first quantization, that you take the tensor product, you construct by hand this tensor product of state, they're non-interacting. But of course, you can make also the second quantization. You reinterpret the Schrödinger wave function no longer as a wave function, but as some operator acting on some Hilbert space. And this is totally equivalent, by the way. They have two linear systems. Of course, the second quantization allows you to go further because it allows you to make interpretation when the Schrödinger is nonlinear. which is something that you cannot do in the first quantization, because quantum mechanics is a linear theory, so you have these kind of things. And quite recently, there are several works, in fact, discuss this possibility to use a concept which is so-called L-infinite algebra and braided infinite algebra to make some quantum field theory of braided quantum field theory. And there is this very clear paper, so there was Richard Sabo proposed a lot of work on that. This is an example. There's a very clear paper here which can give some idea how to go exactly from Hopf algebra to braided infinite algebra. And probably this will be also some way to make some extra construction for braided Majorana-Fermis from this second quantization viewpoint. And that's something which is for sure it is worth to do. And again, and that's it. This is mostly what I wanted to say about that. And I thank you for the attention.
Obrigada, Toppan. A gente vai abrir agora para dúvidas, perguntas que o pessoal aqui no Zoom queira fazer, ou o pessoal no chat, no YouTube também queira fazer. A gente vai começar aqui pela sala do Zoom, então quem tiver uma dúvida pode levantar a mãozinha ou abrir a câmera, que a gente vai organizando. Nami, quer fazer alguma pergunta ou não?
Não.
Por enquanto, não. Deixa eu dar uma olhadinha aqui no chat, só um segundo.
Tá. Bom, eu quero simplesmente dar essa mensagem, porque essa é this sort of things is that it is some brand new approach of some very old topics in a sense, but can give some new information about. And it is really, this is some application of first principle about these braided Majorana-Fermi. When you understand that...
A matéria condensada teve uma revolução, porque agora você consegue fazer uma série de sistemas e você produz partículas que existiam antes só no papel, né? Assim, a matéria... Você tem Majorana-Fermions produzidos em condensed matter?
Experimentalmente, eu acho que você tem que perguntar isso para Múcio. Eu estou, evidentemente, analisando as condições teóricas para produzir eles.
Sim.
E, inclusive, estou tentando de fazer essa junção de vários tipos de parastatísticas. Eu vi, por exemplo, que tem experimentais que estão construindo para-osciladores utilizando ion e laser e codificando nessa forma. Eu posso passar as referências. Achei muito interessante porque isso está muito ligado com o que estou tentando de fazer agora, eu do ponto de vista teórico, mas justamente para achar essa ligação com os experimentais. E por isso que também que enfatizo, uma vez que você entende essa parte teórica de como são os ingredientes básicos, depois tem que entender como manipular eles, to engineer essa estrutura num sistema desse tipo. Parece que é possível, tem boas dicas dessa coisa, mas isso evidentemente tem que abrir uma discussão com os experimentais, que eu pretendo justamente fazer.
Mas no finalzinho do seu seminário, você também falou que pegar a função de onda de Schrödinger e transformar num operador, você citou uma coisa assim, né? No finalzinho do seu seminário.
A segunda quantização?
Isso é uma segunda quantização só, né? Isso que eu não... assim, eu não entendi, assim, isso não seria uma segunda quantização de uma teoria não relativística, só isso?
Olha, a questão é a seguinte. Primeiro, você tem que entender que esse tipo de estrutura do braided é mais complicado da estrutura normal. Porque, por exemplo, quando você faz a primeira quantização normal, você pega uma função de onda, você totalmente simetriza, totalmente antissimetriza, e você não precisa fazer coisas mais sofisticadas, você faz isso na mão. Para fazer coisas um pouco mais sofisticadas, tem que ter uma pequena tecnologia, que não é muito difícil, baseada sobre essa off-álgebra com Profº. Agora, quando você faz isso, você consegue fazer o braiding desse tipo de teoria. Agora, evidentemente, na teoria usual não relativística, você pega a equação de Schrödinger e tem as duas interpretações que são equivalentes de primeira e de segunda quantização. Quando você tem teoria puramente linear, são perfeitamente equivalentes. Tá. Evidentemente, a segunda quantização é mais poderosa, porque você pode pegar uma teoria quântica de campo, tanto relativística como não relativística, que é não linear, e ela tem uma interpretação no âmbito da segunda quantização. Evidentemente, você não pode ter na primeira quantização, porque a função de onda na mecânica quântica é um objeto que é linear, tem que superpor. Agora, um operador...
por exemplo. Condensado de Bose-Einstein.
Um operador não precisa. Agora, você pode pegar no linear Schrödinger e interpretar operatorialmente em segunda quantização. Agora, por isso, tem um interesse, evidentemente, de ir além do formalismo da primeira quantização para a segunda quantização. E pode ser que esse tipo de estrutura, que são a infinite álgebra, braided dell'infinite álgebra, pode dar alguma dica. Eu até falei com meus estudantes que eu acho que é um ponto interessante. Estou tendo várias discussões com o Richard Sabo, justamente a respeito disso, para tentar de entender essas coisas.
Certo. Eu acho que o Múcio quer falar.
Sim, professor Múcio, se quiser ligar sua câmera.
Oi, Toppan, tudo bem? Está escutando?
Oi, Múcio. Escuto perfeitamente. Não estou vendo você, mas estou escutando perfeitamente.
Eu quis aparecer, mas não estou sem câmera. Deixa eu perguntar um negócio. Você, no estado fundamental desses Majorana Fermions braided, né? Quando você toma o limite de n indo para infinito, o estado fundamental desse sistema aparece alguma nova propriedade emergente, ou ele seria um líquido de Fermi? O que seria o estado fundamental desses majoranas, no limite em que n vai para infinito?
Olha, a questão é a seguinte, não sei, bom, eu estava pensando, tem que pegar a função de partição, grande ensemble, e fazer análise, mas para esse tipo de modelos muito simples, onde os majoranas não são interagentes, mas são truncados, lá você pode fazer isso e construir todas essas coisas que dependem do nível de truncamento, evidentemente. Agora, bom, outras questões lá abertas, como eles aparecem na matéria condensada, é outros aspectos que precisa ser investigado, evidentemente. Mas atendo a sua pergunta, mas é tudo a coisa a ser feita, na realidade. Tem muitas coisas a ser feitas nesse âmbito, eu acho.
A minha curiosidade era sobre o estado fundamental, meio teórico mesmo, né? Você tem assim, N partículas não interagentes, né, com essas propriedades estranhíssimas. Qual seria o estado fundamental desse sistema, né? Seria um líquido de Fermi usual, por exemplo, preenchendo partículas até um dado nível de Fermi, ou apareceria alguma propriedade nova nesses devido a essas propriedades de braiding?
Múcio, bom, o que eu posso dizer por enquanto é esse, que se os majoranas são não interagentes, o estado de vácuo de n deles é simplesmente o produto tensor dos estados de vácuo da símbolo majorana. Tá? E isso você pode ir até N que vai a infinito na coisa. Depois, a partir disso, você cria estado excitado. Agora, se você não faz nenhum braiding dos Majoranas ou férmions ordinário, qualquer que seja o número N de Majorana que você pega, você pode criar somente um estado excitado, e não mais, devido ao princípio de exclusão de Pauli. Agora, se você consegue codificar um braiding dele, e experimentalmente, como ele aparece na matéria condensada, tem que analisar mais em detalhe, evidentemente, o tipo de modelo. Lá as coisas são diferentes e são descritas desses truncamentos de parastatística, na realidade, onde os férmions estão diventando alguns paraférmions que podem acomodar, no máximo, até um certo nível de energia, um certo nível dele, dependendo do nível. Não sei se isso responde à pergunta.
É isso aí.
Mas isso é somente que posso dizer por enquanto.
Tá ótimo. Obrigado.
Obrigada, Múcio. Mais alguém tem alguma dúvida, algum comentário que eu gostaria de fazer? Por enquanto, no chat, o pessoal não se pronunciou. Não sei se aqui na sala o pessoal gostaria de falar alguma coisinha. Bom, se ninguém tem nenhuma dúvida mais, nenhum comentário, então acho que a gente pode encerrar aqui o nosso seminário. Eu queria agradecer mais uma vez a participação do professor Toppan. A gente está fazendo esses seminários quinzenais, né? Então, a cada 2 semanas a gente tem alguma apresentação da Cotel com pesquisadores da casa ou pesquisadores convidados. Às vezes a gente vai ter uma programação um pouquinho fora desse padrão quinzenal, mas todos eles estão sendo divulgados por e-mail no CBPF News, estão sendo divulgados nas redes sociais também. Então, o pessoal de fora do CBPF pode assistir, mas presencialmente a gente está realizando na casa esses seminários quinzenais que são abertos ao público para qualquer instituição que esteja de fora, para qualquer aluno que queira participar. A casa está aberta e a gente vai estar divulgando. Queria agradecer ao pessoal que está aqui no Zoom, o pessoal que está assistindo também pelo YouTube. E até o próximo seminário, né, pessoal? Acho que é isso. Se alguém quiser fazer uma consideração final.
Então.
Acho que é isso. Pessoal, muito obrigada.
Um abraço.
Um abraço.
Obrigado pela oportunidade.
Tchau, pessoal.
Até mais.